Hello, my name is Xiaohan Zhang. Today I'm going to present our paper, Cross-View Image Sequence Geolocalization. Most existing cross-view geolocalization methods rely on panoramic Curie images. However, limited field of view images, as known as limited FOV images, are more common. As shown on the right side, we present the coverage area of user-uploaded panoramas and limited FOV images on the Mapillary platform in the Bay Area. It is obvious that limited FOV images are more popular. Motivated by these facts, we combine the popularity of limited FOV images and the range of visibility of image sequences and propose cross-view image sequence geolocalization. Our goal is to geolocate limited FOV image sequences instead of panoramas. Since no existing dataset satisfies our needs, we collected the first large-scale cross-view image sequence geolocalization dataset. The coverage map is shown on the right side. In summary, the collected dataset covers more than 500 kilometers of various roads in Vermont, USA, including the urban area, suburban areas, and highways. It contains around 118,000 ground images. We then employ a greedy algorithm to segment the long sequences into short sequences. In the end, the dataset contains 38,000 satellite sequence pairs. To tackle the problem of cross-view image sequence geolocalization, we propose a baseline model. The model takes a sequence of ground images as input. A VGG16 with shared parameters extracts raw features for each ground image. Inspired by the recent success of the transformer, we propose a temporal feature aggregation module to learn the temporal correlation among the input sequences. A final ground feature is summarized by an averaging pooling layer. We also employ another VGG16 to extract features for the input aerial image. Finally, the model is trained with a soft margin weighted triplet loss. In real-world scenarios, the number of ground images can be varied. To tackle this problem, we propose sequential dropout, known as SD, which drop out ground images by a random mask. As shown in this slide, we fill 0 in index 1 and index 6, which means that frame 1 and frame 6 are dropped out. During inferencing stage, we can simulate different sequence lengths by filling zeros in certain position. Here, we fill in zeros in index 0 and 1 to drop them out and obtain a sequence with a length equals to 5. In our experiment, we choose Safa and Vega as our baseline. We also ablate our model with or without SD. As we can see from our experiment, our proposed method outperforms all the baselines, and training with SD can largely boost the performance. We then compare our model training with or without SD by feeding Curie sequences with variant lengths. The blue bar is a model training without SD, and the red bar is a model training with SD. The results show that training with SD suffers less performance degradation while the length of the Curie sequence is decreasing. This demonstrates that the model can learn a more coherent feature representation. To sum up, in this paper, we propose a new end-to-end approach for cross-view image sequence geolocalization. We put forward a novel large-scale cross-view image sequence geolocalization dataset. We propose a novel temporal feature aggregation technique, and we propose a new sequence dropout method to predict coherent features on sequences of different lengths. Thanks for watching.